All right, it's 1 o'clock. I think we are ready to start. So, good morning, good afternoon, or good evening, depending on which part of the world you are connecting. My name is Giacomo Persi Paoli. I am the program lead for security and technology at Unidir, and it's my pleasure to welcome you to the first of a series of 3 webinars organized by Unidir and UNODA with the purpose of exploring different aspects related to lethal autonomous weapon systems. And hopefully the timing of these webinars is well placed given the GG on laws that COVID permitting should take place next week. This first webinar will focus specifically on technical and technological issues of autonomous weapon systems, with a view to address some of the aspects that have been identified as requiring further analysis and insight. First of all, I'd like to thank all of you who submitted questions in advance by email. And I take this opportunity to remind you that you can still do that by email for the webinars scheduled for tomorrow and Wednesday on military and legal aspects, respectively. If instead you have further questions for our technical experts today, please submit those using the chat box throughout the event. Don't wait until we open formally the Q&A. Depending on how the conversation goes, we might simply try to inject your questions as we go through. So in order to facilitate a common kind of technical understanding and support further dialogue within the GGE, we're convening this webinar really try to unpack and further investigate technical aspects of laws through 2 separate lenses. In the first part of this webinar, we're going to be looking at particularly the kind of the algorithmic lens, or the AI core behind autonomous weapon systems. The second part, instead, we will focus on more the system integration issues. So what are some of the challenges or the things to keep in mind when integrating AI and algorithms into physical weapon systems? And this is because, you know, the title of the GGE refers to lethal autonomous weapon systems. It's not the GGE on military AI. So at some point, even though AI is a clear kind of core element of laws, at some point we need to go beyond talking only about AI and starting to analyze also how AI is integrated into physical weapon systems, which, as we will discuss later today, opens up a whole new range of issues and challenges, but also potentially opportunities to learn from other experiences that have been accumulated in other applications, civilian applications that have been looking at autonomous systems. Despite the fact that I'm an enthusiast of this subject, I don't have the ambition of being able to answer all the questions by myself. In fact, I'm counting on the substantive contribution of a number of great speakers that will help us navigate this fascinating and uncertain field of study. I'm just going to briefly introduce them, and then, of course, as the conversation progresses, I'm sure you'll be able to learn even more about them. We have Dr. Vanina Martinez and Dr. Ricardo Rodriguez from the University of Buenos Aires. We have James Pinelis, who is the Chief for Test and Evaluation of AI and Machine Learning at the Joint Artificial Intelligence Center in the US. We have Professor Barry O'Sullivan from University College Cork. We have Thomas Grohs, who is the Chief Engineer for the Future Combat Air System project at Airbus. We have Dr. Gabriele Rizzo, who is the Principal Futurist at Futures Lab. And last but not least, we have Abhishek Gupta, who is Machine Learning Engineer at Microsoft. So we really assembled this very rich and very diverse panel to really try to capture different perspectives on this issue. The way this panel is going to work, we have a series of guiding questions that have been put together, combining those that we received from you, the audience, with others that we have prepared after reviewing all of the most recent reports and national submissions that have been made in the context of the GGE to really try to extract what are the questions that could really help, if answered, advanced discussions. Of course, the GGE has been going on for many years, and we have only 2 hours, so we're not, while we hope to answer as many questions as we can in a satisfactory manner, it's very likely that this is just the beginning of a much more detailed technical discussion. But hopefully, through this webinar, you will leave this webinar in a couple of hours from now with a better understanding of what are some of the opportunities, but also limits and limitations that are inherent in the concept of autonomy and autonomous weapon systems as we know them and see them today and in the foreseeable future. Because one of the aspects that we would like to discuss today is also, while certain, there is the tendency to extrapolate certain trends in the future and say, well, if we're able to do this today, then in 10 years, we're clearly going to be able to do much more. While that might be potentially true in theory, there are some practical barriers to further developing AI capabilities that we would like to discuss today. So, without further ado, allow me to remind you once again, if at any point during this webinar you hear something that is unclear and you would like to ask questions, please use the chat box. We have a whole team here that is monitoring your questions and will inform me promptly if anything is submitted. So I'd like to start this webinar by asking Vanina and Ricardo, can you please help us understand what are algorithms capable of doing today? So what kind of tasks can they reliably accomplish, and what kind of tasks do they still struggle with? Vanina, you want to kick us off?
Sure. Yes, we were just discussing that with Ricardo and hoping that you'd give us the first question to us. Thank you for inviting us. So one thing that we wanted to remark about this is that the notion of algorithm as we know it, like a sequence of steps that we program into a computer so it performs a task. It's a little different when you think of AI algorithms. In this sense, machine learning algorithms are somehow meta algorithms. They do not express the exact sequence of steps that the machine should come up or should perform to realize a task, but it rather gives the framework to the computer to find out the algorithm to perform the task. So I think that's important to make the difference in this sense. Whatever we say about algorithms, we have to think if it really applies to an algorithm that creates algorithms. So that's just to start with it. And then if we talk about AI models and AI algorithms that implement AI models, the kind of tasks that we see they perform really, really well today are tasks that primarily have to do with very basic cognitive tasks, as cognitive tasks, and they actually like vision or voice recognition or natural language processing, not so much understanding, but creating human readable text. Most of these tasks are, as I said, like very narrow tasks, like they are very well at performing that specific kind of pattern recognition. But we're going to talk about this later, but then it's hard to transfer that they're performing to a bigger task or different tasks that seem to be related. But like especially in vision, these algorithms are really good and actually better than us. They have other capabilities that humans don't have because they can manage other kind of data that our brains and our bodies cannot even detect. So in that sense, they perform better and they actually can do other tasks that we can't. I don't know if Ricardo want to say something about
it. You're still muted, Ricardo?
No, I agree with Vanina. We prepare this part of the answer.
Thank you. I'd like to, Abhishek, you were nodding when Vanina was making her remarks about the fact that, that there might be a difference between processing and understanding of what the machine is doing. So would you like to elaborate a little bit on that, and particular, maybe link to this? What are, in your view, given your expertise, what are some of the kind of inherent and insurmountable, if you want, barriers or limitations that we have today in the use of AI? Are we ever going to achieve a 100% reliability or 100% predictability of AI systems?
No, absolutely. And I think, of course, I'm glad that Vanina made the distinction between processing and understanding, because I think that's one of the things that gets lost in translation when we move from these sort of technical discussions to, higher level policy discussions, where we blur the lines between some of those distinctions. And the reason I was nodding was because I remember this incident where machine translation was applied to some comments on the Facebook platform. And because of this very distinction in being able to process text versus in being able to understand text, an individual's comments where he said, good morning, were actually perceived as trying to incite violence on against a particular minority in the country that they were in, and that led to physical action in the real world, where police showed up to his doorstep and had him arrested, and he had to explain that this was a mistranslation of what he had posted. And so, again, when we're talking about this in the context of using these sort of diverse data streams to gather intelligence, in the sense of getting accurate machine translations. I mean, even when humans do translations, a lot of the nuance can be lost when you're moving between different languages. And certainly today, machines aren't capable of doing that. Yes, we can parse out tokens and talk about certain entities within the tokens. We can identify nouns and subjects and verbs and all of those things. But when it comes to understanding the entire context and nuance, that's still something that isn't really fully feasible just yet. And so that's one place where we need to be really careful if we're incorporating that into our decision-making process.
Thank you. Are there any other observations on this kind of a capping? Please, Jane.
So, Giacomo, I thought it was interesting the way that you asked that question, because the way that you asked that question was, can we ever hope to achieve 100% reliability and safety and things like that? And I think in practice, it's somewhat unlikely, but I also don't really think it's necessary, right? Even when you're talking about warfighting applications, we've never fielded a system that's 100% effective at everything it needs to do. And our biggest autonomous agents, who are humans, are also not 100% effective at everything that we need them to do, nor 100% reliable. I think the two questions, so there's a spectrum of reliability that we might hope to achieve. And it's also the decision to delegate some kind of an authority or decision-making to a machine is not a binary decision, right? It's a continuous decision. And as we learn more about what these models or algorithms are capable of and where they perform better and worse, certainly as far in the future as I can see, the human is still in the loop and can take on the remainder of that piece, right? So that's what I wanted to comment on. Back over to you.
Thank you for that. It was a kind of a provocative question that was trying to understand there is clearly different perception of what is the level of tolerance for unpredictability or unreliability when we're dealing with a human operator or a human decision maker versus a machine. Clearly, the 100% is, you can aim for it, but it's very, very unlikely that you reach it. But I see so Gabriele and then Barry on this. Gabriele, over to you.
Yes, thanks, Giacomo. I'd like to build on what Jane was saying on we don't need 100% reliability, because I'd like to very, very strongly stress the fact that AI doesn't have the concept of causation. So whenever we say because, we are doing something that's more than what AI can do right now. So every time we are making sense of something that comes from the external world and we're giving it a meaning, so the sense making of what's in the external environment, we're doing something that machines can't, because machines, as Vanina was pointing out, they can correlate. They can say, it looks like. That's what they can do. And in a very strong and thorough and unimaginable way right now, because they can make sense of data and not of the content of, for example, let's talk about image classification, right? They can make sense of the data that's in the image, not of the content that's in the image. They're looking at levels of colors and tiny bits of data that we can't see, so we can't make sense of them, but machines can. So they can very, very well and fast go in the look-like mode, but they can go in the because mode. And that is why we will never, in the short term, be able to substitute humans or to substitute machines. And that is why we need to think in terms of a convergence of the two.
Barry.
Yeah, good afternoon, everybody. I suppose I want to go back to the question of what can algorithm do and what can algorithm not do. And I suppose before even addressing that, I just want to talk about what is an algorithm. So I suppose today, in the context of AI, mostly what people talk about when they use the term algorithm are the things that are the outputs of machine learning systems. So they are methods, sets of rules, neural networks, all these sorts of things, but they are essentially functions that take in some data and give a result. And that could be identifying something as a member of some class, predicting a value, but invariably these systems are trained and not programmed. So they're trained with data. So when you hear people talking about data-driven AI or machine learning, this form of algorithm is essentially trained. It's taught, and there's a few things you need to be aware of in that context. First of all, the algorithm is only as good as the teacher. So it's only as good as the data. It's only as good as the choice of data, and they have vulnerabilities. So if a machine learning system has not been given examples of a particular scenario, then it has no way of knowing how to act in that scenario. And so one of the fallacies that non-experts often fall foul of is this idea that artificial intelligence is intelligent. Artificial intelligence is not intelligent, it's just simply in the way that you or I are intelligent. It mimics intelligence, it gives the appearance of being intelligent. So if you use one of these methods in a particular scenario, it can make mistakes. And absolutely none of us are perfect, but these algorithms are only as good as the data that they're trained with. And of course, they are also susceptible to attack. So for example, the data can be poisoned. The scenarios that they experience in the world can be mischievously made look like scenarios that correspond to good examples. So that's something that one needs to be very, very careful of. On the other hand, there are programmed algorithms. So the good old-fashioned algorithms of computer science. And these are programmed, and you can prove properties of them, and you can prove correctness of them. But this is not the case in data-driven AI. With data-driven AI, there is always an uncertainty. There is always a possibility of error, and they're only as good as the data that they're trained upon. So yes, there have been great successes in game playing. There have been great successes in image recognition. There have been great successes in speech recognition. But there have also been very convincing examples of how these systems can fail. They're very, very brittle. So I think in deciding whether one deploys one of these algorithms or not, one has to really understand what they are, what the limitations are, how they were developed, how they were tested, and knowing that in a trained AI, in a machine learning AI, there are no guarantees of accuracy. Thanks.
Thank you. And I just would like to kind of pick a couple of things that were said that we're going to be using those to link us to questions later on. But first of all, a point that Jane made that I think it's really important is this fact that we are used to hear or references to autonomous systems as if they are either 100% autonomous or 0% autonomous, meaning that the human is either in control or fully or not at all, while in fact there are a range of options in the middle. And I'd like to later on to discuss about this and the fact that some systems may have autonomy in some of their functions, but more human involvement or supervision or engagement in other functions doesn't make them less autonomous in a way. But we'll get to it later. And I'm also pleased to report that we already see more questions coming. And of course, the questions are somehow at the intersection between the technical and the legal and the kind of military policy domain, as we can imagine. So we'll try to cover as many of those as we can. But if you're not happy with our answer, please remember that there will be a military and a legal panel after this. So I just wanted to, Abhishek, you have your two fingers up. Before I move on, please, over to you.
No, and it, I guess, sort of relates to one of the questions that you mentioned, but also the point that Jane and Gabriele had brought up as well. And when you have humans who are still the arbiters of the final decisions that are taken, when you get inputs from the machines, I think one of the things to consider is what meaningful human control in that situation looks like. And the reason I bring this up as an important point of the discussion is because there are these two notions that sort of cover this, which is the notion of automation bias and the other notion of algorithmic aversion. And automation bias basically refers to this idea where we become increasingly trusting of the decisions that come from these autonomous systems because they've been right many times in the past, and we assume that they will be right in the future. And that's just, it's a cognitive bias in a sense from a human perspective. And algorithmic aversion, on the other hand, is this notion where we choose to not trust the decisions of the system, even when they can be right and humans are wrong. And so there's the recognition that both of these things happen, and then sort of tying that in with the notion of, as you said, we can't achieve 100% certainty in terms of the decisions that are put forward by these systems. There is a degree or there is a confidence interval around the predictions that are made by these systems. And I think what's important to understand, at least from the humans who are in the loop, is if they understand what that confidence interval means. And often what we find, and there are numerous studies that are done on this, that humans' understanding of probabilities is flawed at best. We don't really do well when you tell someone you're 60% sure or 70% sure. I really can't tell what the difference there is. And to be able to use that meaningfully in the decision that you're making, I think is very important. And so keeping that in mind, I think it's important that we don't use a human in the loop or human on the loop in a sort of token human fashion and really empower them in making informed decisions. And I think that's something that we need to be careful about when it comes especially to the use of humans and the context of autonomous weapon systems as well.
Jane, so you have a hot pursuit on this, please.
Yes, I couldn't agree more. And one of the things we talk about, since I'm a tester, right, for the Department of Defense, what we do is test the autonomous systems. One of the pieces that we test is the human factors piece, is the human system integration piece. And one of the components of that is what we call trust calibration, which is exactly what Abhishek was talking about. The idea that if the user trusts the system too much, they get complacent, they get lazy, and they might miss an opportunity to intervene when it's necessary. On the other hand, if the user trusts the system too little, or what Abhishek called algorithmic aversion, then the user perhaps is so busy making up for what the system is supposed to be doing that they shed their other tasks, which are important. And so for that reason, it's really important, I think, when we talk about trust, and I use that word very loosely because there are too many definitions of trust, but when we talk about a trust that a user has in the system, the idea is not to necessarily to build it as much as to calibrate it correctly and to say, here's where you should trust the system decisions, here's how much you should trust them, and here's where you should not. And that's a very interesting line of research and a lot of good work happening there.
Yeah, and we're going to talk specifically about testing and evaluation because there is also a lot of interest in the audience. So, and also at that point, would like also to ask you to elaborate a little bit more, because I like this idea of trust calibration, and what I'm like to know, and actually there is a question that just came in, is trust by a user is, by nature, trust is a very subjective thing. So how do you make sure that, different users, these different human operators and users kind of operate with the same level of expected, trust or expected reliance on the machine? But please, let's not jump the gun. We get there eventually, but please pin that in your mind. I just wanted to, before we move on, I see that Thomas has joined us. I just wanted to make sure that he can hear us and see us correctly.
I can very well hear you. I just can offer you a video from my side. So
that's fine. That's fine. As long as you're with us, that's the most important thing. So the next question that I have, okay, given this kind of introduction, what do recent advances in AI and machine learning in particular mean for possible military applications and military use? Or if you don't have information or knowledge about the military application of AI, more in general, can you help us through kind of concrete examples understand, what is science and what remains fiction today? Because of course we read a lot, we hear a lot in this kind of media-driven information space where there is a lot of information out there, but it's difficult to distinguish between potential that is scientifically based and theoretical and hyped and potentially actually doing almost a disservice because it attracts the attention of the non-expert reader to scenarios that, while can be theoretically possible, as of today or in the foreseeable future, we know that there will be practical issues and barriers that would prevent us from reaching those. So, who would like to have a first go at this? Where is the line between science and fiction, and particularly where do we see the most promising kind of potential for military application? See, Thomas, you have raised your virtual hand, so why don't you go first?
Thank you, Giacomo, and really thanks for having me today.
Can you please speak a little bit closer to your microphone?
Very happy to do so. I hope it's better now.
Yes.
Okay. yeah, what is fiction and what is science, and where are we aiming it from a technology point of view? I think fiction for me is, we all remember those nice Hollywood movies where you have unmanned assets flying close by to a manned asset, and they interact like talking to human beings to each other, and go in a common direction and follow common tactics and really exchange on a voice, and even not only voice but also on a data communication in a similar manner. So I think this will still need some time to get there, and we are by far not there due to various reasons. One might be simple certification rules. If you go into flight safety critical topics, at least having AI-supported undeterministic algorithms is still a difficulty that certification areas are still struggling with. How can we deal with it? But where all of this can help with is, of course, accelerating certain processes. So if we talk about the observe, orient, decide, and act loop, then having such kind of algorithms that are able to digest big amounts of data, do sensitivity studies, and give options for a potential human being as a user to allow him going in the one or the other directions, that are for sure things we can go for. And also within a limited perimeter of autonomy, handing over the control within that perimeter to an automated asset is for sure possible, but still not in that high autonomy level as we know from those Hollywood movies so far.
Barry, you raised your pencil. Go ahead. You're on mute. Sorry.
Thanks, Jacopo. So I think there's a few things that are still in the realms of fiction. What's called artificial general intelligence is still in fiction. So I think when people think about AI these days, when they read about it in the media, they think that the successes of AI mean that AI systems, because they can achieve superhuman performance in one task, they're therefore very good at other tasks. That's not true. So that's so this idea that AI's or general purpose is still somewhat fiction. I think the concept of AI, of artificial general intelligence, whereby we build AI systems that can, solve a multitude of tasks in a similar way to a human being, I think that's very much in the realm of fiction. It's certainly true that we can build systems that have human level capabilities for particular tasks. So we can combine, vision with control, with natural language processing, with planning. But these are systems that are engineered by bringing together separate components and separate functionalities. The AI system itself isn't holistic. I suppose the idea of consciousness in AI is not something that's is still in fiction. Obviously the philosophy community spend a lot of time thinking about the impact of conscious AI, normally considered in the context of ethics. But we're still not there yet. In fact, I'm not sure we would even recognize what a conscious AI would be. Maybe a little more close to the scientific versus fiction boundary is the idea of highly robust AI. So lots of AI systems are quite brittle, as I was saying earlier. If you take, for example, recognizing people's faces when they're wearing COVID-19 masks, I think we're all probably surprised at the fact that we can recognize people very, very easily. The other day I met someone I hadn't seen in 20 years. We were both wearing COVID-19 masks, but we both recognized each other instantaneously. I'm not sure if any AI system we produce today that is trained to learn to recognize human faces could do that, even though we find it very, very easy. I suppose on the science side, we have very robust algorithms for building systems that automate or replicate features of human intelligence. So the ability to plan, the ability to interpret images, the ability to make decisions. But of course, they're all limited by either their programming or their training. And so these systems should be treated as with a degree of, I suppose, cynicism a little bit maybe, because while we might recognize that they are exhibiting something that's highly intelligent, they're normally just exhibiting highly optimized performance in very narrowly defined tasks. So I suppose hopefully that answers some of the question. Thanks.
Thank you. Jane?
I think it's important to mention here, because I think I somewhat know what this question is about. And so just to make it very clear, lethal autonomous systems are still fiction, right? We're working on autonomous and AI-enabled systems in the defense space, in the warfare space. But we're not yet anywhere close to producing a system that we can test in a way to completely ensure that it's perfectly, reliable, that it complies with all the ethical principles that at least the American Department of Defense has adopted. And so until we're there, lethal autonomous systems and lethal autonomous systems remain fiction. And probably a reasonably far in the future kind of fiction. So Skynet is still fiction, which is a question that I get a lot. With that said, at least the American Department of Defense, we have a regulation, the policy number 3000.09, that governs if such a system were, to come online. So the department has been planning for this for many years. And so there are all kinds of government hoops that we'll have to jump through, and all kinds of limitations and laws and policies in place that we would have to abide to before we ever get there. But today we're still quite far away.
Thank you. Gabriele?
Yeah, all great points here. Just a one bit of addition. What military applications of AI are, as of today, are empowering the human. We are shortening the time to make a decision. We are broadening the number of options and the aperture that we can deliver to decision makers. So we're allowing the military decision makers or operational decision makers or whatever, not at the strategic and political level, because it's not yet possible, and it's not in the realm of possible. It's not a state of the art, let's say. It's a state of the possible. So what we can do is tightening the OODA loop, what Thomas was talking about, so we can observe, orient, decide, and act quicker than we could if we didn't have an AI system, but we are not able to substitute the human. We cannot take the human out of this loop. What we can do is putting the human on this loop, so accelerating his way of making sense of the environment so that he can make better and faster decisions.
Vanina, over to you.
Yes, I just wanted to comment on to Jane's comment, and also I just saw a question related to what I was going to say. So what's the definition of an autonomous lethal weapon, right? Maybe Jane can explain it better, but we can say that is a system that autonomously it can decide for a target, act upon that target, and basically execute a mission, a lethal mission on it. What I was wanted to say is that I agree with Jane that Skynet is science fiction, but that doesn't mean that we cannot today build a system that would put together, as Barry said, different pieces of AI and a physical device like a robot or vehicle, and make that a weapon that could be lethal and could create a lot of damage, because exactly as Jane said, we don't have any yet. We don't have any. We're not mature enough to create these machines in a reliable way. So I think that's something that it's important for the discussion. But because that doesn't mean that we cannot make a lethal weapon that may cause a lot of trouble and a lot of damage, and we can do it today. It would be like putting different models of AI together, like stitching it, something like a Frankenstein maybe, and that would be a problem because we don't know how it would behave on the real world, in the physical world.
Thanks, Vanina. I know, Abhishek, you have something to say. I'm just going to plug in a couple of additional questions for you or for Jane or anybody who would like to intervene. So one is, what is the difference between autonomous and fully autonomous? So when we're saying that lethal autonomous weapon systems today are still science fiction, do we mean fully autonomous weapon systems? So those that can, at least my working definition of fully autonomous weapon systems are those that are able to basically implement the full targeting cycle from maneuvering to the battlefield, finding a target, confirming that the target is the one that should be engaged, conduct all of the pre-engagement checks, do the engagement, and then reassess after the attack the results. That's kind of the entire cycle for me is fully autonomous, but because some of these steps may have a varying degrees of human engagement, supervision, or involvement, then that is the difference. But I'd like to know what you think between fully autonomous and not autonomous, and autonomous and fully autonomous. And then just to follow up on something that Vanina and Jane said, we're talking here about state use of this technology and the fact that states, and Jane, you brought up the example of the US that was quite proactive in setting forward like parameters and conditions around the development and then use of these technologies. And I'm wondering, I'm just throwing on the table, like for non-state actors or actors that may not be interested in achieving a level of ethical, legal, and technical compliance with these systems, if the technology today would allow these sort of actors that operate outside of internationally accepted legal and ethical framework to do more than a state would. But Abhishek, over to you.
So I just quickly wanted to add one point in terms of, I think, determining the capabilities of systems and how rapidly this field evolves in terms of what we're able to achieve. And I think one of the exemplars for that is what's been possible with GPT-3. And of course, I'm not just talking about, and for those who don't know, GPT-3 is the latest large-scale NLP model, pre-trained model rather, that was released by OpenAI, and has had some impressive demonstrations that have come out, notably the one Guardian article that was put together, though of course the rebuttal after that was that it put out 8 pieces and human editors spliced together the best components together to create a composite article. But I think some of the other pieces of impressive uses of that, which serve as examples for what I want to say, is that people have used that, combining it with other pieces of technology, for example, to do things like describing a website layout in natural language and have it generate all of the necessary code to create that website. In other things, what they've managed to do is to integrate that into the parsing of legal documents to surface relevant clauses, which help them in sort of automating away the work of paralegals. And so the point that I want to make here is that the progress paths are not linear, and sometimes you can, by moving forward a step in one direction, you open up some orthogonal areas of progress which are not evident until you get there. And so when we're talking about what is on the border of science, reality, and fiction, we also need to be aware of how certain advances can open up sort of these orthogonal areas of progress in an instant which previously we weren't able to imagine. And quickly, I'll just say one point on your comment in being able to distinguish between autonomous and fully autonomous systems. I think when we're talking about autonomous vehicles, I think the taxonomy that they've created there in terms of going from level 1 to level 5, I think does a pretty good job in making it intelligible to people when they want to assess what the degree of autonomy is, what the limitations are, and what the capabilities are. And I think adopting a sort of similar taxonomy, and not that it doesn't already exist because NIST has some standards around that, but I think breaking that taxonomy down into something that's intelligible for people is going to be important, especially from a policy-making perspective, where if you have very dense, arcane standards, it can be hard to parse and make those distinctions.
Thank you. And yes, I see a few other hands raised. Abhishek, can I ask you if you can take a second to, if you can, just post on the chat a link to this taxonomy that, I don't know, maybe people would find interesting to have a look at. And I go to Gabriele and then Barry.
Yeah, back to the point of laws, meaning lethal autonomous weapon systems. And I mean, autonomous and fully autonomous, we could make the argument of, yes, a fully autonomous is a weapon system that can go through the whole kill chain, so the F2, T2, E2A cycle, that find, fix, tag, track, engage, exploit, assess, cycle that is from the start to the end of the engagement. But are we able to imbue this system with all the principles that a military commander or an operator should be able to bring to the field? So and I don't want to cross the line towards the legal part. But for instance, necessity, proportionality, distinction, and humanity. Are we able to do that? We are not. So in every part of the kill chain, and especially in the engage and exploit, there has to be the human part. And that's why we should stop thinking of what we can do with machines alone, because in every part of this process, there will be a human coupled with it, as much as it is in other fields. But I know what we will end up talking about this later, so I'll save the questions for later.
Thanks, Barry. You're on mute.
Yeah. So I suppose on the question of autonomy and automation and all these sorts of things, like on the science fiction question, I suppose one of the challenges we have in this particular space is one of definition. Artificial intelligence is a term that's been around since the mid 1950s, but there isn't an agreed definition of artificial intelligence. And I think when we talk about lethal autonomous weapon systems, there isn't really a universally agreed definition of what a lethal autonomous weapon system is either. And of course, then we put autonomy in here, and there are many different interpretations of autonomy. And I suppose when we want to talk about these things at the level of your discussions, that creates lots of challenges, obviously. Now, it might be interesting to consider compiling not necessarily an agreed list of definitions, but an index of how these terms are often used. And of course, these definitions could be conflicting, but I think it's useful to sort of see where the overlap and the commonality is, because then it sort of helps focus the discussions to some extent. Yeah, so I understand when Jane says, for example, that laws are still fiction, I can understand why she would say that. Of course, one could also see the weapon system as something that non-state actors could develop with a drone, with a very rudimentary vision system that's capable of executing a terrorist mission, for example. And I think in the public mind, at least, that would satisfy the definition of a lethal autonomous weapon system. Then the question is, what does autonomy mean? Like typically in artificial intelligence, autonomy means motivated agency. So, but of course, as we said at the beginning, AI systems are in no way conscious. So, normally what we mean in practice when we talk about autonomy is the ability of a system to carry out an action without human intervention. So, Abhishek gave some nice examples in automated driving, for example. So there are well-defined sort of hierarchies of autonomy in self-driving cars. We're all used to this kind of stuff. The car that can do the cruise control, the car that can do the automated parking, the car that can do the automated driving. We can see that these are more sophisticated. So, but when we start really getting down to the definitions, that's where the challenge happens. And so my advice always to forums that are grappling or dealing with these issues that don't have universal agreement as to where their scope begins and ends is to gather together with all the possible definitions, and at least that gives a possible, that sort of scopes the uncertainty. That could be very, very useful.
Thank you, Barry. And there are two more questions I'd like to discuss before we move on to the system part. We already started to kind of touch on the system integration bit, but there are two more questions I'd like to ask. I see, Thomas, you still have your virtual hand raised, and I don't know if it's leftover from your previous intervention or if you want to add something at this stage.
It was really, sorry, it was really a leftover from the previous one, so I need to find out how to get it.
Okay, so the two questions that I have are one that emerged from, well, came from our participants, which is about the criticality of the issue of data and the fact that the question reads, the GGE has broadly ignored the data question, and would panelists see value in the GGE also discussing data? For example, how countries are collecting, preparing, and storing, securing, whatever, the data that will be used in their systems. So, data is fuel. Data, in another analogy I've heard, is, data is to AI the same thing that ammunition is to rifles. So you can't really use one without the other. So, as experts and specialists in this field, can you really have a discussion about autonomous weapon systems, lethal or otherwise, without talking about data? Who wants to go first? Vanina.
The state of the art of AI today is based on models that learn from data. So the weapons or the systems that we are going to build today and in the next years are going to be based on this kind of models. So we cannot leave the data issue behind. And I really liked one analogy that Barry did at the beginning, saying that these models are going to be as good as the teachers they have. So as good as the data they have. So it doesn't really make any sense to start to talk about how reliable and trustworthy the systems are if we don't look at the data, how we collect the data, how we curate the data, and also the issue of data availability, because there may be some tasks for which we don't have the data, and then that might be an issue that they may not allow the system to behave in any predictable way. So I think it's crucial to talk about the data, because these models are based on data, the data that we create, and it's data that we didn't create for the system. So it's data that we have, that we use, that we generate for different purposes. And then there's a lot of issues there on how to manage, how to collect, how to curate, how to make the whole process of data management to train, validate, and test these kind of models in a responsible, transparent way, that it's also part of the characteristic of trust that we want from these systems.
Thank you. And can I ask, Jane, as part of your work as testing and evaluation, and data, I'm assuming is a key component in here. So how do you go about the algorithm and the data that goes with it? Do you make distinction? Do you treat them as a whole?
So there are some distinctions, certainly, but I can give you at least some elements of our framework that govern how we deal with it. First, we've recently implemented at the JAIC specifically, we've implemented data cards, right? So now, and this is part of us trying to follow one of the 5 ethical principles that the department has adopted, which has to do with traceability. So we always have to trace, why are we getting access to certain type of data, who provided it, how it was collected, how it was provided, for what purpose, what kind of elements are in the data, that are potentially flags for misuse, right? Because this is one thing, I know this is a forum specifically focused just part of what we do, right? Weapon systems just part, particularly at the Joint Artificial Intelligence, a lot of missions that have to do with warfighter health, that have to do with humanitarian assistance and disaster relief, et cetera. And that's where a lot of these other data sensitivities come into as well when we're dealing with health data, particularly personally identifiable health information and things like that. So there's a lot of policies that govern just that one piece of the data that we worry about. Now, on that, we actually have a separate team at the Joint Artificial Intelligence Center whose sole responsibility is to deal with data and everything that has to do with data governance, data storage, data preservation, data sharing, things like that. On the test side specifically, we do, of course, worry about preserving, especially, certain test data sets, right, where hopefully they're both representative somewhat of the training data, but also of the operational data on which the system will be used. And of course, it's very important for us that our vendors who provide us with AI-enabled systems are never exposed to that data, so that we keep testing objectively and independently to see how these systems work. So yes, absolutely, we do a lot having to do with data governance. The Department of Defense recently has appointed a chief data officer within the Chief Information Officer's office. So there's a lot of offices there. We take that very seriously. Additionally, one of the ethical principles that we go by is equitability, where we worry about unintended bias. And so data has plenty to do with that as well, because your tool is going to perform based on the data that it was trained on. And so you have to be able to summarize that data very well so that the user knows at the other end, this model was only trained in such and such environments. It will only, we characterize its performance in such and such environments. It should not be used outside of those environments, or at least its performance outside of those environments is unknown. And to that extent, test and evaluation basically guides TTP's tactics, techniques, and procedures of employing these systems and concepts of operations that have to do with employing these systems. It's on us to very carefully characterize, where the system performs and where it doesn't, and that mostly has to do with the data that it was trained on.
Abhishek, thank you, Jane.
Yeah, and sort of building off of what Jane said, I think, of course, the importance of data can be, emphasized enough. I think one of the things that we must also pay attention to is how robust, from an adversarial ML perspective, we can make these systems. And a lot of that also hinges around us being able to, as we were saying, talking about data availability, in being able to source some of these examples that are handcrafted, that can trigger unintended behavior in these systems, because there's ample research in the machine learning security domain where utilizing adversarial examples actually does help to create more robust inferences and to be able to source and actively utilize those examples is very important. In the context of weapon systems, there was a recent example where when we're talking about drones that are automatically trying to detect different objects on the surface in terms of targeting, applying a certain pattern of paint on the objects that are on the ground triggered misclassification on part of the recognition system on board the drone. And what's interesting there is that that can sort of be utilized in two ways, right? One, you can conceal, sort of military targets, which is, camouflage, which has been done forever in terms of masking, potentially sensitive targets. But the other side is you can potentially paint or try to trigger a misclassification on civilian targets in order to lure an entity to commit a war crime where it's not permitted to deploy weapon systems on civilian entities or non-military, non-combatant entities. And I think that's where it's interesting in terms of gathering sufficient data, especially of the kind that triggers this sort of misclassification, so that we're building ML systems that are robust to these adversarial attacks.
Thank you. I have a follow-up question in relation to data, which is the following. So, you as a group of experts, could you see? So one of the main issues in our audience here and as part of the GGE is the ability to use and deploy autonomous weapon systems in respect of international law and international humanitarian law. And I'm using this language carefully because I don't want to work with the assumption that it's the system itself that has to respect international law and international humanitarian law, but rather the combination of the human that makes the decision of using it and retains some level of control, and the system, so applicability of IHL in international law is key. Do you see a benefit in potentially creating like a common or an internationally agreed or a shared training data set that tests different scenarios that are based on international humanitarian law, and then this data set is tested and improved, and it could potentially become sort of like a benchmark tool that each member state that is interested in developing this sort of capability could then use in the context of weapons reviews, for example. Because right now there are, the reason this knowledge isn't readily available to all. So any takers, Barry?
Yes. So I think having such a data set or data sets would be extremely important for a variety of reasons. I suppose there are lots of challenges raised by AI-based weapon systems, and one is knowing whether they have been built properly, whether they have been evaluated properly. And I'm sure Jane can tell us a lot about her work. But of course, in order to be able to have conversations internationally about the performance of weapon systems, one needs to have some sort of data set, some sort of baseline to talk about. And I think if the community can develop such data sets and be able to exchange information about the performance of systems on these data sets, or be able to say that the system achieves in excess of a certain level of performance on these data systems, or accuracy in itself isn't enough. Maybe also to be able to talk about what kinds of errors those systems can make. Now, of course, the challenge with sharing information about errors is that it can be exploited. One can create adversarial examples that exploit those features. But I think beginning to have some sort of common language for talking about the behavior and performance of AI systems in military applications would be very, very welcome. And this comes down to things like shared data sets, common data sets that are agreed and people are comfortable using. And I think that would be a major advance. I think would be very, very welcome. Just as an aside, I've put into the chat window a few links. The last one being a link to the recent European Commission's white paper on AI. And I only flag that because when you look at, so that particular white paper talks about how the European Union is going to regulate AI systems, non-military AI systems, so commercial AI systems. And they talk about this distinction between high-risk and low-risk AI systems. And if you look at the high-risk AI systems, almost all of the requirements that the Commission envisage are around issues of data, robustness, record keeping, human oversight, and so on. So I think I'm not putting it there because, well, yes, I am a European, but I'm not putting it there as a great example of something that one should do, but merely as an example of a framework that puts a lot of emphasis on data.
Thanks, Barry. I see Thomas and then Jane.
Thank you, Jakob. Yeah, I would definitely agree with the colleagues that such kind of a central data set would be good to have from a verification and also from a validation perspective. I'd rather put it in a broader focus that with the data set, I would also like to see some kind of common requirements ground on those requirements. Whatever system is designed to fulfill those requirements will be used with the data together, so that we have basically the chain from the requirements originally established to the final verification somehow guided in that process. And let's say some ethical requirements handbook might be actually something good to have for a designer in hand for the basic principles. And then with such kind of a common data set, it could be tested against that with the application of the AI that it fulfills those basic requirements. But of course, also looking at the comments in the chat, if those data sets are known, you could specifically design to fulfill those, but it's actually not mandating that the broader sense what the data actually wanted to trigger is really dealt with. So we still need to be differentiating between just designing to fulfill this simple test and not keep in focus the original sense behind it from an ethical or a legal employment of such kind of force, that this also needs to be considered. So there is a certain danger with that as well, that systems will just get designed to satisfy this kind of data stream, but neglect other topics which are of a greater sense behind it that will not be captured.
Thank you, Thomas. Jane.
So a couple of things I'll mention here, just based on what everyone has said so far. One, common language. At least for us, even just in the US, it was a challenge to come up with a common lexicon for, at least for testing artificial intelligence. I'm happy to report that we've done so. We have it written down, at least with the US. And we've now shared it, at least with our Australian partners, and we've shared it all across the department here. It took us a few months to come up with all of the definitions. And frankly, I think there's still a couple of blanks in there that we're working to fill. The Joint Artificial AI Center has recently kicked off a collaboration with 13 other countries. And I believe since we've kicked that off, a couple of other countries have joined us as well, to try to exactly foster that kind of international collaboration that was just discussed. The focus, it was a two-day long conversation, primarily focused on AI policy and AI ethics. And there was some in there on human-machine teaming as well that I think addresses just many of the things that we're touching on here. In regards to a focused data set, we recently kicked off a collaboration with another country, just to see if their tools can be used on our data and vice versa. And so I think we're starting to move in that direction. I think the concern is valid that if the parameters of the test data set are known, then one could train a model that performs well on that test data set. I would argue that if your test data set represents the operational environment very well, then that's not necessarily a bad thing, provided that you've clearly articulated, what this model is meant to be doing and where and how good it is at that. If you plan to take that model out of that context, then of course, then you should test on a broader test set as well. Okay.
Thank you for that. And I think we're now, moving into the second part quite seamlessly, which is great, about system integration, because right now we've been talking a lot about AI and what it can and cannot do, but we already started to refer to the system issue because, you know, all of these debates are interesting, but at some point, if we're talking about integration of AI into autonomous systems, you know, weapon systems or otherwise, we have to consider it as a package. We have to consider it as, you know, the sensors and communication devices that are responsible for collecting the data from the environment or receiving the data if it's sent by like another location, and this data is then fed to the kind of the AI or the algorithms. And then, you know, once the algorithm kind of does the processing and makes a decision or, you know, elaborates and determines a course of action, then this course of action has to be transferred to, you know, physical actuators or, you know, to actually have an effect on the environment. Otherwise, we are remaining in the realm of the AI. And we got some questions during the preparations of this event around, you know, what is the difference between autonomous and automated. I'm going to try to give you and just ask to intervene if I am scientifically extremely inaccurate, or if you can live with this working definition, please let's go with it. So the difference is that automated systems, you know, operate based on rules, and there are responses that are triggered directly as, you know, the classic logic, if this then that. So if this happens in the environment, if this sort of information or data or observation is made, then do this. So it's a deterministic approach. It's a rule-based approach that, you know, but in fact, automated and autonomous weapons are probably, you know, they're not either or. There are probably two ends of a spectrum where, you know, autonomous, it's based on machine learning. It's based, like Vanina said at the beginning, like macro level algorithms that then allow the system itself to come up with its own rules. So what is the, you know, what are the challenges? And, you know, we have the luxury of having experts from different fields here. So what are the challenges of coupling, you know, these advanced algorithms in complex physical systems, you know, that have to then be deployed in the field? And I'm going to be using, for this second half of the conversation, I'm going to be going back to the examples of autonomous driving that was raised by Abhishek earlier. I'm not saying that the civilian world can provide solutions for military problems, but it can certainly provide source of information and lessons that have been learned that could then be used or leveraged in the, you know, in advancing discussion in the military domain. So, you know, to take the example of Tesla is probably a decade ahead of everybody else in their conceptualization and testing and manufacturing of autonomous driving. However, you know, not long ago, there were videos circulating about how it continues to systematically fail kind of autonomous driving, autonomous braking functions. And, you know, so clearly there is a problem when you are trying to integrate even a very sophisticated and reliable algorithm into a physical system that has to interact with the environment. Can you help us understand what are some of those challenges? Who would like to go first? Jane, please.
I'll kick us off, at least. I think from the tester's perspective, which I tend to be more sympathetic to, the challenge becomes the state space explosion, right? Because now you have a system. Ordinarily, the way that I would like to design a test, right, is I think, okay, these are 10 factors that tend to affect my system performance, and so I'll design a test that varies these factors systematically in some kind of an operationally meaningful way. And at the end of the test, I can tell you, okay, well, under such and such factors, different combinations of factors, perhaps the model performs or the system performs in a certain way. When you get into some of these autonomous systems, it becomes considerably harder to test them, because as they become systems of systems, and some of their operational parameters are unknown, or we're just bad perhaps at specifying them. In some cases, we don't know what kind of environments they might be exposed to. We don't know exactly what might affect their performance and behavior. In case of systems that make decisions, we don't usually know how those decisions get made. And we don't know what the edge cases are, right? What is the very unlikely thing, the black swan kind of thing that can trigger, something really bad, especially. And so, or just disruption of performance even. And so it's that state space explosion that makes things very challenging as we try to figure out, if we don't know everything that affects the performance of the system, and we in some cases don't know exactly how it makes decisions, then how do I properly test it to build the case of assurance for the system, so that I can, in the end, to tie it back to what we were talking at the beginning, so that I can calibrate the trust that the warfighter should have in that system under different conditions.
Thank you, Barry.
Yeah, I think I liked your definition of that distinguishes autonomy from automation. I think I suppose one way of maybe simplifying it is the following: that the difference between autonomy and automation is agency. And so what I mean is we can have something that, an electric kettle is an automated system in that it knows when, at a point it turns off the power. However, if you've got something that has the agency to decide how to carry out the action, then you're into the field of autonomy. And I suppose the level of the sophistication of the agency and the sophistication of the task essentially define how autonomous the system is. I suppose one thing I would add into your definition, or maybe have alongside the definition, is that there's automated and autonomous, but these are orthogonal to notions of responsibility. And so, so I mean, sometimes people talk about autonomous systems as systems that are where a human is in the loop or a human has control. That of course is important, but it's orthogonal to the notion of autonomy, and it's on the axis of responsibility. So I think when we go so if you draw two axes, I think you could have as one axis going from automated to autonomous, and then lots of levels of autonomy, and then on the other axis you have basically control up to responsibility and liability. And I think it's important to think about those two dimensions simultaneously, because as the system becomes, and maybe there's even a third dimension, which is the impact of the system or the risk. And so in this sort of three-dimensional space, then you have all the possible things you need to worry about, from not only from a control and autonomy point of view, but also from the governance and the responsibility and so on. So that I would simply add in that notion of responsibility, and we're in good shape. But that's alongside the definition. Thank you.
Thank you, Vanina.
So one of the things I wanted to say about coupling AI systems with the physical system, I think has to do with this notion of testing. So testing is not really will not give us the guarantees that the software, the piece of software and physical device would actually do exactly what we wanted to do. So testing is supposed to cover. So you're supposed to define an adequate battery of tests that will give you a very good idea of how well the system behaves with respect to your expectations. But this kind of systems are so complex within themselves, as Jane was saying, and then you, on top of that, you put this these models, AI models together, working together within a physical device. What you would really, I mean, we may discuss if this is what we want or not, but if you want to really make sure that the system is actually predictable, you have to verify and validate the whole construction of the system, and to give some theoretical guarantees that the system actually behaves in the way that the programmer or the designer actually thought it might. And then the whole area of research in verification and validation, where you actually can have correctness guarantees, it's not really mature in regards to AI models, right? So as Barry said in the beginning, so for algorithms, the traditional algorithms, there are techniques for that. When we want to transfer that to AI systems and coupled with physical devices, then it becomes very, very hard. And testing is not enough to show, to actually guarantee the predictability of the system, of the correctness of the system.
Thank you, Vanina. I see, Thomas, you have a follow-up, please.
Thank you. And picking up on what the colleague said, I think for me the key critical part is to define those environmental key parameters that if they are violated, an automated system will have to, let's say, call for help, if I may call it that way. So a human being will always be able to do so. So if you feel uncomfortable, you basically call somebody else. Can you help me on this? And how do we implement in an automated system that it recognizes I'm out of my boundary conditions, and at least out of some key boundary conditions that I'm not allowed to go beyond. And from there, basically to see what is another way I can reorient myself. To implement that will be quite interesting to see, and I'm sure there are already solutions available that could be implemented. But also from a testing perspective, to exactly identify those key parameters against which we need to test such kind of a system to show if it extrapolates beyond that, is it still capable in a certain reasonable way to perform, or at what point is a breakup or a break-off point where we need to cut and say, okay, in that sense, the automation will have to be stopped, and either it's mission abort or whatever else we consider the necessary action that falls out of that.
And thanks for that. And I'm just going to take this opportunity to ask a follow-up question, which somehow links with something that was raised by the audience. So I'm going to start again. I'm going to go back to the example of autonomous driving and the fact that we want an autonomous car to drive autonomously, but we also want an autonomous car to be able to detect and identify a traffic light and know that when a traffic light is red, it should stop. So the fact that a system may operate autonomously, it does not mean that its behavior cannot be constrained by rules. So the fact that rule-based approaches and machine learning approaches are sometimes be considered as binary alternative to each other is not necessarily the case. They can coexist on the same physical system. And this is kind of the context of the question, which is, if we're thinking about weapon systems and autonomous weapon systems that need to be deployed on the battlefield, those constraints are those of the legal constraints of international law and international humanitarian law. So the question is, how far can we go in encoding or in prescribing some of those boundaries already at the system level, so that it can trigger, we can think about the rules of engagement, but you can think also of how translatable are certain principles of international law into rules that the system can understand, and not necessarily, maybe the easier rules, or like a rule of engagement that, prohibits you to go outside of a certain area, providing that the system has a reliable GPS signal. It's something that it could implement on its own. but there might be more complex ones where the system might be operating outside of the so-called kind of comfort zone and may require for help, for authorization to proceed, or whatever. So, to what extent can today systems be, the behavior of systems, weapon systems, can be kind of constrained by some of these rules? Any takers? Please, Gabriele.
Yeah, I mean, I hear a lot of times that we're kind of moving from the point of how deterministic we are from the point of how complex we are. And that is exactly the shift that we have to understand here. And I'm not sure that is super clear to also the audience. So just to be very, very short, an automatic system works based on a given number of rules, because the environment that it is facing can be broken down in a finite number of possibilities. So you have basically a rule for each possibility. Whenever you're facing the actual environment, then the actual environment is much more complex, in the sense there are so many possibilities that you cannot simply list all of them. And moreover, there are possibilities that are interacting with one another. So you cannot list all the possible states that you might be facing, but you have to rely on the point, as Barry was saying, the point of agency. So on decision, on behavior. And the shift is from a system that is doing something because it was told to do something, to a system to which can ask, why did you do that? So we're moving more towards the part of explainable AI. So why did you predict this? What are a finite number of dilemmas that you can articulate so that I can trust your decision? I can make sense of the prediction that you did. To your point, the gamut between automatic and autonomous is not black or white. So we can integrate rules in autonomous behavior and the kind of rules in autonomous behavior. And that is what we did, actually, for example, AlphaGo did. You don't have just a single AI that is tackling the whole complexity of the game, but there are several different avenues in which the situation is channeled depending on some conditions, and then there's autonomous behavior there. So that is a possibility, of course.
Thank you, Vanina.
Just to make sure, because I think it was raised in the audience as well. So there is within artificial intelligence, there is a wide variety of models that are not machine learning, and that are also the basis for autonomous agents. So we have planning, we have argumentation, we have satisfaction constraints. There is like 40 years of work in artificial intelligence that it's not machine learning. That also, like if we want to build systems like a weapon based on those models, they will also have many of these problems, right? But so I mean, there is like Gabriele was saying, it's not black and white. So it's not that you have a deterministic case by case algorithm that can implement the system, because just the environment doesn't allow you to do that. But there is a whole spectrum in the middle of things that you can do to constrain machine learning, not allowing the system to learn from the data, but to behave based on certain parameters of knowledge of how the world behaves, how this specific environment behaves, what it's expected for the system to do. And I think that is in the combination of these AI models. And I think it's important because then to think about this and the possibilities that there can go beyond that. There's a kind of a new area in AI that it's called neurosymbolic artificial intelligence that actually tries to combine this building blocks like learning, planning, and try to come up with more robust AI. It's still in its infancy, but I think that's one of the ways in which we can actually constrain AI systems, like feeding knowledge and not data.
Thank you, Vanina. And I'd like to ask you all one bridging question before we enter the last part, which is I really want to have a more in-depth discussion around verification, validation, testing, and evaluation, because I think it's important. But I want to go back to something that came up at the very beginning, which is the role of the human in all this, and the fact that in discussions on laws there is often, or more than rarely. More often than rarely, a discussion on implicit assumption that, as I said earlier, a system is either 100% autonomous or not autonomous at all. So how does the different level of control that humans retain on the system as a whole, or on individual tasks that the system is performing, how does that, change its classification as autonomous or not? Should it change? I mean, is there like it looks like from what you're saying that while potentially technically feasible, at least from what I understand, it doesn't seem to be any appetite for the development of a system that cuts off the human completely, because from an application perspective and a deployment perspective, there isn't necessarily an added value that such a system would bring. So could you help me better understand, what are the human machine kind of touch points and interfaces that are possible? Barry.
Yeah, so as I was saying earlier, I think that for me, automation and autonomy are on a different axis to responsibility and control from the human side, from the human perspective. I personally believe that humans always need to be responsible for the deployment of AI systems. That's just a personal view. So in my view, there needs to be someone who is ultimately responsible for the AI system when it goes wrong. So I'm not a military person, so I can imagine that might be the commander, or it might be whoever it might be. But I think these issues should be considered separately. I think because there are certainly applications of AI where while there might be a human who's responsible for them, a human never actually intervenes. So for example, the Netflix recommender system. So Netflix recommends us a bad movie. We don't need to get upset about that. We just ignore the movie, right? So, and it's an autonomous system in the sense that it decided what movie to recommend us. There was no human beings involved in that process. But of course, nor did there need to be any human being sort of in the loop of checking if that's the right movie to recommend to Barry. So I think these two dimensions should be considered separately. And I think also that's why I think it's helpful to think about this, about these as separate dimensions, because it allows us to think about maybe different policies we should be applying in different settings. So you can imagine a situation where there's potential loss of life. There's another dimension to this, which is maybe a third dimension, which is civilians, competence, and so on. And maybe one wants to deal with that differently. And the level of human oversight over an autonomous or automated system in a civilian context might be significantly higher than it would be in a competent situation. I don't know if that's true, so I shouldn't probably try to give military examples, but I think treat them separately, I would say.
Thank you, Barry. Any other takers on this point on kind of human machine, Gabriele?
I don't want to look like I'm a broken record here, but the point of human and machine, to me, it's crucial to understand the scenario. And moreover, I'd like to point out that there has been a record in the past with in chess, for example. At a certain point in the past, it was around 2007. It was shown that if you put together a system that is made up of an international master and an algebraic manipulator for chess, you systematically beat any other grandmaster, and you systematically beat any other chess for software. So it's the convergence of the two that is really the best out of the both worlds, and that is something that can make the best of both capacities. You take the capacity for analysis, for ingesting of big data, of sifting through this ocean of data from the machine, from the machine cognition part of the tandem, and you take the ethics and the moral and the direction from the part of the human. So in this sense, human and machine, as long as they are trained, and there's the great point about trust calibration from Jane, as long as they trust each other and you are on that fine range where you are not relying too much on the machine and you're not fighting too much the other part, that is the way to go.
Thank you, Gabriele. Abhishek.
So yeah, building on that, I think again, it's important to understand, borrowing the phrase from Gabriele, that not to sound like a broken record, but the level of understanding that the humans have who are a part of that composite human machine system. The point there being, we can look at the Air France accident that occurred, where there were signs that were provided by the autopilot system, handing back control to the humans. It's just that the humans were no longer well equipped to take over, and were misinterpreting the signs that the system was providing in terms of being able to take back meaningful control, which ultimately led to the unfortunate and fatal crash. My point here being that as we're developing these composite human machine systems in a domain like chess, of course, there's no harm to life, but in a situation where you're controlling an aircraft, if the humans have never over manual control and to correctly interpret the signs that are being provided in those failure scenarios, you're basically rendering useless the inclusion of the human in that system in the first place. And I think that training and education is very, very important as we're interleaving humans and machines together. Because without that, we're going to end up with more situations like the Air France incident, where even though they were being provided the signs that something was wrong, it's just that they had never had the experience before of being able to take over control and to guide the plane back to safety. And the black box records show that the Air France flight had a chance of being saved. It's just that the humans took too long to act, and they were confused amongst each other with the signs that were being provided. So again, I think the training and education part is going to be critical.
Thank you for bringing that, because that's a key component also of any transition between a piece of technology and the military capability. If we look at how all the different elements that constitute a military capability, from doctrine to organization to training and logistics and material. So the material part is only one bit. So the piece of technology is just one of the elements. But for that piece of technology to become a usable military capability, there has to be much more around it, and training is definitely a key component of that. Any other points on human machine interface or touch points? If not, I'd like to spend the last 20 minutes or so on something that we, as I said, we kind of touched upon kind of continuously throughout the panel, which is, VMV or TNE, so validation, verification, testing, and evaluation. And my question is, to what extent these processes and procedures can be used to address concerns over predictability, explainability, reliability of autonomous weapon systems? Because, from the non-expert community, they're often, these processes are looked at as a kind of a silver bullet, but I'm assuming they're not. They're very good for something and probably not good for something else. So it can maybe starting with Jane, can you help us better understand, what we can expect VMD and TNE to do?
Sure. I'd love to start this discussion. So you used several terms in there, and I kind of want to carefully address all or some of them. The way that we think about test and evaluation of AI-enabled systems in the Department of Defense here is through, building an assurance case basically over time. So we have now, whereas for physical systems, we were able to have, potentially a big test event at the end, an operational test, and certify that, yes, this tank can go this fast and shoot this accurately. As I mentioned previously, the state space explosion, and also just the way that software systems are built in general, where there's a lot more interaction with the user throughout the development process, it means that we kind of test over time. There's no one big single test event at the end. And so as we get through that process, we do look at some of these things. The first is kind of testing the AI tool by itself, where we have reserved test data that our AI vendors never get to see, and we test that tool against that data for things like accuracy, for things like vulnerabilities and things like that. The next step is the system integration step, which you mentioned previously as well, where we now have this shiny new model that operates as part of a system of systems. Oftentimes, the other parts of that systems are legacy platforms that were not necessarily meant to interact with AI systems. And so there are a lot of interesting things there where we look at things, reliability that you mentioned, that was probably the first time that we start looking at that. Reliability being a very technical term for statistician, right? As we look at mean time between failures, and does the AI-enabled system, crash everything around it, or how long can it function before it shuts down or does something that it's not supposed to? And then you talk about predictability and explainability, which to me falls under the next step, which is the human factors step. And I think both predictability and explainability are interesting terms to talk about, because to me, they're the different facets of what we very loosely call trust. But trust, again, I don't think it's the right term. I think probably predictability is what I want the warfighter to have. My sense is that the warfighter doesn't need a detailed understanding of why the system does what it does or how the neural network works. The warfighter needs to have the confidence that if the system has this input, he or she is going to get this output, with a certain level of confidence. Not necessarily all the time, but perhaps most of the time, and at least they know what conditions make that vary and how much it can vary. Mm-hmm. Explainability is a deeper requirement, right? It's a bigger requirement. And it's a hard requirement to place because of intellectual property concerns, right? So the Department of Defense wants to work with the best, the brightest vendors like Microsoft, like Amazon, like Google, like others. Those vendors tend to be concerned about their IP, and there's only so much of how their model works that they want to disclose to us. And that prevents at least some of that explainability. But I would argue that, again, we don't need 100% explainability. We need to instrument these systems enough to where we understand where the key decisions are being made and perhaps what are some of the things being considered, so we can collect that data during test. And that information really is only relevant to the tester. That information, I would argue, doesn't need to be passed on further. So that's what I'll say about explainability, and I don't think we require 100% of it. Plus, if you think of deep learning, you start getting into trade-offs between model performance and explainability, where you might be able to fit something very tightly to exactly the problem that you have at hand, but you no longer know exactly the magic that happens to get you to that predictive state. And so I would say that with all systems, hardware and software systems, the job of tested evaluation is not to build trust, it's not to build explainability, it's to quantify risk, right? And then it's thankfully above my pay grade, as we say here, for decision makers to say what level of risk is acceptable. And that level is going to vary widely depending on what system you're designing. If it's a system that helps you deposit a check, you might accept one level of risk. If it's a system that potentially could be turned into a lethal system, it's a very different level of risk that you might be okay with, and so is going to require very different amounts of testing. The maturity of the science behind testing AI-enabled systems, we're still learning. And I would argue that probably the development of these systems is outpacing our learning on how to test them, which is a little bit worrisome. And we're making a big argument inside our Department of Defense for much more funding to be allocated to research and development of test tools, so that by the time these systems are ready to go, we're ready to test them, and so that testing doesn't become a bottleneck between the development and getting the warfighter what they need.
Thank you for that. And I see Abhishek has a hot pursuit there. I just wanted to stress one point that I think it's very important, that you make the distinction between kind of the concept of explainability and the concept of understandability, in a way, which is something that we elaborate on in our recent report, the Black Box Decoded, which we released just over a month ago. That kind of invites, in a way, member states to move their attention from explainability, which is very, very technical and perhaps unnecessary, to the concept of understandability, which refers to the ability of the human to understand what the machine will be doing, which is, it's a little bit, it's not just semantic, it's a fundamental distinction between the two. Abhishek, over to you.
Yeah, no, you sort of stole my thunder there, I guess. I was going to mention the same thing, that I think, explainability is a very technical concept, and what I was going to phrase it as was intelligibility. They both sort of mean the same thing. And there's this very interesting sort of taxonomy that you can create there in terms of who you're tailoring that explanation for. And thinking about whether it's the engineer who is building the system, who requires a great degree of technical detail so that they're able to tweak or amend the system in case of failures or making improvements. And then there are the operators of the system. So you build a system, you sell it, and then someone actually operates that system. They require a different level of explanation, which tells them what the capabilities and the limitations of the system are so that they can operate it effectively. And then finally, there are the subjects of the system. So who is the system being used for or on, though I hate to use the word on. And they require an understanding of how they might, let's say, alter their behavior so that they can, perhaps correct, let's say, a misclassification that's allocated to them. So if you're talking about, loan applications and you're denied a loan application, what is it that you can do as an applicant to change that score? So the explanation that you require there is again different. So thinking about it along those three lines, I feel makes for a good case in terms of bringing that very technical notion of explainability to something that's sort of implementable in practice.
Thank you, Abhishek. Barry, do you have a comment?
Yeah, just a few things about this. I suppose a lot of the public discourse and the public policy making that's going on around AI starts from an ethical point of view, and then it tries to figure out, well, how do we build AI systems in order to satisfy these ethical requirements? And that's a very noble thing. But if we think about the airplane, I don't think explaining to somebody how the airplane works necessarily increases our trust in that system, right? So I'm not even quite sure physicists know how planes fly, to be perfectly honest. But we trust in air travel because we trust the people who build the systems, and we trust the methods by which they do so. And we trust the testing and the evaluation mechanisms. So I think we need to be putting more emphasis into the how systems are built rather than abstract properties that they should have, you know? So I think like these are engineered systems, and I think we should, you know, I think it's right and proper that we focus a lot on the validation, verification, testing, and so on. The other questions of whether they're explainable or whether they're transparent, I think these are less important in general. They might be important in specific situations, but I think what's more important is that systems can be built in a way that we trust, that we test them in a way that we trust, and that they can be reliably deployed. So, for example, things like adversarial attacks are unlikely, that we can prove some properties of the system to ensure that they are robust. I think that's what we should be really focusing on, because if we hold up explainability as an absolute requirement, I think we compromise on the other things as a consequence, and I think that's in general quite dangerous.
Thanks, Barry. And I just want to close this question with reflecting on a comment that was made by Pascal in our audience, which is the principle of risk quantification seems quite close to what all military leaders do today. And I'm assuming from what I've heard today, that's true. I mean, as long as the military decision makers are equipped with the information and knowledge that they need to make the decisions, then the autonomous weapon systems, in that respect, once you enter the kind of a risk management approach, they're just another tool that they have at their disposal, assuming that we get to the point where autonomous weapon systems will be made into an available military capability. But yes, like the risk management approach, or the risk-based approach is the same. And I'm going to conclude and just ask you like a 30 seconds intervention, if you can, on one question that might be perhaps beyond your immediate field of expertise, but I think it's very important because we've touched on the issue of trust, particularly with respect to machine and operator. The question that I have here is, how far do you think that testing and evaluation can go in, or how effective of a measure can it be to build trust and confidence among states? So we've touched, previously on the issue. Wouldn't it be great to have a commonly generated data set that could be used? So for testing and evaluation, so that everyone is kind of using the same, but kind of following on this train of thought, what it is, testing and evaluation, trust and confidence building measure for AI. How far can we think of it in that context? Who wants to have a go? Vanina.
Based on what everybody already said, I think that verification, validation, and testing are absolutely necessary. What I think it's would be a problem to like a gap from that to actually build a trust is that in general, software systems, I mean, there are some standards and But there's kind of a soft regulation about how these methods of validation and testing and verification are done. I think that it would be interesting to see how we can actually create the development of these systems, the process of development, to make it actually the whole thing trustworthy, right? And for that, we need some other kind of framework in which we can, using verification, testing, and validation, we can actually translate that to the users, to the buyers and the users and other members of the community that want to use the systems or need to use the system. So I think there's some gap there, and I don't really know how to maybe to express it, but it's not a rigorous. There is not today software systems, and not to talk about AI, but softwares in general, not really built that rigorously unless they are like high risk, right? So I think there's something there we still have to work on to actually build the trust that we want.
Thank you. Gabriele, 30 seconds, and then Abhishek, 30 seconds.
Yeah, to build trust across the community, you need a shared understanding and a common ground. The common ground could be that data set of data about theater to which you want common responses from your AI systems or for your autonomous system. The shared understanding has to be built. There are several communities. There is, for example, the P7000 communities in IEEE. That's about the ethically aligned design of autonomous and intelligent systems. It's a buzzing community. There's tens of several subgroups that are working on several topics around giving out principles so that the design of systems, not just weapon systems or autonomous systems, could be along the lines of shared ethics.
Thank you, Gabriele. Abhishek.
Sort of building on that, I think one of the important things that I see that's going to be important going into the future is alignment in terms of legislations and use of these technologies across nations as well. And I think that will come from a shared vernacular, not just in terms of the technical language that we use to evaluate and test the systems, but also a shared understanding of what these principles mean. Because these principles are often quite high level and abstract, and they can be interpreted in various ways. And so having that sort of cross-cultural collaboration across nations is going to be very important, especially for those that are trading partners, where they might exchange technology, labor, knowledge, etc. And for them to have a shared understanding. Otherwise, it'll start to even hinder the free flow of that across these nations.
Thank you. I see Thomas, 30 seconds, please.
Yeah, rather approaching the topic from a more operational point, I think all the customers I'm talking to are basically asking for coalition force operations capability. So doing a common test and evaluation and verification of the functionalities for me is absolute key to enable this kind of common operational ground. So this will heavily be fostered by that common testing before going into a live engagement.
Thank you, Thomas. I'm determined to finish on time. So before I give the floor to our silent and guest, Ambassador Drzynski, for his final remarks, I just wanted to thank all of the speakers for an incredibly engaging and enriching conversation. I'm all of you in the audience for submitting your questions. I'm sorry if we didn't manage to cover them all. I just passed the link to our feedback form. Please do take 30 seconds to fill that in. And the session has been recorded, so we will be posting it on our website along with the list of all of the sources and resources that were posted in the chat box, so you can all find them in one place. It's been a great pleasure to be the host of this event today, and Ambassador Drzynski, over to you for any final remarks that you may have. I hope you found this useful for your work.
I think that I can comfortably say in the name of the whole group of experts that this has been really an excellent exercise in viewing both our process, but what we've been discussing over the past few years since the beginning of this as a meeting of experts. Abhishek mentioned this loss of distinctions in the beginning, and I think that from time to time, perhaps this has been done, but at the same time, we use this phrase of a greater granularity last year, and I think that we have achieved a lot greater granularity over the period of the GG. Trust calibration, Jane mentioned it as an important process, and it was something that came up as well as the possibility of having this trust calibration as an international cooperative exercise, perhaps a common data set that is then tested within a given theater, different contexts, tested, retested, and then used as a tool, as one tool. But Giacomo, you put it very well in saying that it's not just about the weapons, it's not just about the technology, it's about the people who are the humans who are part of that phrase system or in the substance systems in it. I think that it's really an amazing start. I look forward to tomorrow as well, and certainly the military considerations need to be based on what is technologically possible, what comes out from this. These conversations are related, and it's really an important way of us building this common understanding. So the gratitude, not just as chair, but I think of all GG to have this really view from the side on what is being done within the GG and how we can, in common, all together, with all minds engaged, do this so that we really make it a good process with these emerging technologies that are certainly complex to say the least. So gratitude from my side, and I look forward to tomorrow, and sincere gratitude to all the panelists who participated today, and Unity for organizing it today, and ODA tomorrow's webinar. So, bye, thanks.
Thank you very much, and thank you all again for coming, and we will be posting this recording online soon. Thanks.
Thank you. Bye-bye.